All right. We finished chapter 2. Now we jump to chapter 5, which is system of linear equations. In this chapter, we talk about when you have two equations with two unknown or two variables, and then three equations with three unknowns. That's as far as we go. We do not get into how to solve it with matrices. So basically, section 5.1 is what we're going to cover in this chapter 5. Okay, so let's look at the slides. Here's 5.1. Systems of linear equations. System of linear equations, introduction, unique solution, undeterminate solution, and overdeterminate solution. We're going to see what they mean. And matrices, again, as I said, we are not covering this part, right? We just talked about system of linear equation, which is 5.1. System of two linear equations. So here's two linear equations. Ax plus by equal h, cx plus dy equal k, where a, b, c, d, h, and k are constant. So as you can see, the only two variables you have is x and y, right? X and y. So what we're going to do is come up with the solution that satisfies both of these equations. So we come up with a value for x, a value for y, that when you plug it into both of these equations, the left-hand side will be equal to the right-hand side. Two linear equations would give you two lines when you graph it, right? There is three possibilities when you have two lines graphed. One is the two lines cross each other at some point, right? At the point where they cross each other, that would be the common solution. And that is what we are solving for, if we can solve it for the common point. So the intersection is the common solution with the coordinates of x and y. That's what we're going to do. Two lines can be parallel to each other. That means they never cross each other, right? So if they don't cross each other, then there is no solution. Because they never cross each other, there is no common point between them. Another possibility, the third possibility, is that two lines are basically the same. They lie on top of each other. So there is infinite number of solutions because there are infinite places where they cross each other. In common there are many solutions. So here is one possibility. So you have line 1 and line 2, right? They cross each other at this point. They cross each other at this point. Again, this point would give you an x value and a y value, right? The coordinates here, x1 and y1, is the solution to the solving of the system of equation with these two lines, right? So here you would have a unique solution because two lines can cross each other only at one point, because this line 1 keep going in this direction and this direction, so they'll never meet again, and line 2 goes in this direction and this direction, so they never meet again. That is different when you have for example two curve. For example, you may have this and then this, so these two cross each other at 2 points, right? So if we had a nonlinear system, then this would give you two different answers. But as I said, here we are talking about linear equations. So this is out of the scope of this section. The relationship between two lines, as I said, might be like this. So here's line 1, here's line 2. they're parallel to each other. When they're parallel to each other, that means they don't cross each other at any point. There is no common point between the two lines. So when there is no common point, there is no solution. So that's the second possibility. The third possibility, when you have a system of linear equations, system of two linear equations, is when the two lines L1 and L2, let me see, L2 is in blank. Let's see where blank is. And L2. They are right on top of each other, so they have many common points, infinitely many solutions. They are the same line. Okay, so you have 3, 1, 2, 3. 3 different possibilities when you are talking about two linear equations, a system of two linear equations. Here's an example on how to solve it. Y equal 3x minus 2 and x plus y equal 10. Y equal, let me change the color here. Y equal 3x minus 2 and x plus y equal to 10. Right? One way to solve this is you figure out the value of y as they have here. They made it simple for us. You figure out the value of y in terms of x, which is this, and then plug this into the second equation for y. So when you do that, the second equation will become x plus, in place of y, now we put 3x minus 2. That would be equal to 10, right? So this is how our second equation would look like. Then x plus 3x minus 2 equal 10. Then 4x minus 2 equal 10. Take 2 to the other side. 4x equal 12. X would be equal to 3. That's the x value. If you plug x equal to 3 into one of these equations, again, it would be easy to plug it into number 1. Then y would be equal to 3. In place of x, you put 3 minus 2. Then y would be equal to 9 minus 2. Y equal 7. So that means these two lines cross each other. This is line 1. This is line 2. These two lines cross each other at the coordinates of 3 and 7. At the coordinates of 3 and 7. Okay. If you use your calculator or online graphic calculator, you can see that they cross each other at 3 and 7. Now, this x of 3 and y of 7 satisfies both of these equations, equation 1 and equation 2, because it is in common. So here is, again, here is x, here is y, right? X is equal to 3, y is equal to 7. So for example, if you plug in for y in equation number 1, you plug in for y 7 equal 3 times 3 minus 2. So 7 is equal to 9 minus 2. And 7 is equal to 7. So it satisfies equation number 1. In equation number 2, where you have x plus y equal 10, x is 3 and y is 7. So 3 plus 7 should be equal to 10, and 3 plus 7 is 10. 10 is equal to 10. That's how you know they cross each other at this point. Now, if I was going to graph this, I can do this. y equal 3x minus 2. 3 is the slope of the line and minus 2 is the intercept. The second equation, I can write it in the form of slope-intercept. That means that is y equal minus x plus 10. So that's the second equation. The slope is minus 1 and the intercept, y-intercept, is at 10. So if I go ahead and graph this, x here, y here, okay, here is 0. For the first equation, if we say, well, I think I'm gonna, let me clean this. For the first equation, I'm gonna give different values to x and figure out what y is. So for example, y equal, let's say x is 0, so 3 times 0 minus 2. So when x is equal to 0, y would be equal to minus 2. That's one point. Another point, when y is equal to 0, how much is x? Again, dealing with the first equation. So that would be 0 equal 3x minus 2. That means 3x is equal to 2. That means x is equal to 2/3. So when y is 0, so these are 2 points. One point is x of 0 and minus 2 for y. The other one is 2/3 and 0. So I can plug that. Well, let me do equation number 2 also. Equation number 2. So here's equation number 2. This one or this one, it doesn't make any difference. When x is equal to 0, y is equal to 10. So 0 and 10 is 1 point. When y is equal to, so that's one answer. When y is equal to 0, x would be equal to, when y is 0, x would be equal to 10. Right? So 10 and 0. So x and y, we need to go all the way to 10. So let's say here is 0, here is 5, here is 10, here is 5, here is 10, here is minus 5 for y. I think you got all the points. So to graph the first one, I have to show this point with 0 and minus 2. 0 and minus 2 would be on the y-axis. This one is 0 and minus 2. This is 1 point for the first line. The other one is 2/3 and 0. If this is 5 and this is 0, 2/3 is less than 1. Probably here. So that point is 2/3 and 0. If I connect these two together, this would give me line number 1. This line number 1. Line number 2, x of 0, y of 10. That's this point. X of 10 and y of 0, that is this point. You connect these 2 points together. This is line number 2. The intersection of these two happens at, I forgot, what did we get for the answers? The intersection of these 2 points, I think y was 7 and x was 3. 3 and 7. So that's kind of like a graphic representation of these two lines, line number 1 and line number 2, and their intersection. This is the common point. So the two lines cross each other, therefore they have a unique solution. Again, the unique solution happens at the x of 3 and y of 7. All right. Let's clean this up. And as usual, look at the slide and see if we, based on what we did, we can follow the slide and come up with the same solution, which is x of 3 and y of 7. It should be the same thing. So this is one, the relationship between the two lines where you have a unique solution. Okay, let's see what they did. Again, in the second equation, they plug in for y, 3x minus 2. Substitute 1 into 2. Then 4x equals 12, x equals 3. And once you solve for x, then you solve for y, and y would be 7. So the solution for this system of two equations and two unknown is 3 and 7. X value 3 and y value of 7. Same thing we got with a little bit more explanation. Now here is another system of two equations, two unknown. Again, the unknowns are x and y, and both of them. And now you have to solve for x and y. Okay. Now this time let's solve for y in the second one, in the second equation. Keep y on this side and take everything to the other side. So y would be equal to 2x minus 4. That's from the second equation. Now for y, plug into the first equation for y this value. Plug it in the first equation. So first equation now would read 4x minus 2. In place of y, we put 2x minus 4 equal 8. Now 4x minus 2 times 2x is minus 4x plus 8 equal 8. So 4x and minus 4x would cancel. You have 8 equal 8. Now this is a true statement. This is a true statement, right? 8 is equal to 8. Now, there is nothing to solve for. There is no h to solve for. If this happens and you end up with a true statement, that means these two lines, line 1 and line 2, are basically the same line. And therefore, there is infinite number of solutions, right? They are the same line, therefore there is infinite number of solutions. Now, you could have seen that. Look here. If you go ahead in the second line, and multiply everything in the second line by minus 2, your second line, multiply everything on both sides by minus 2, so the value does not change. It would, what do you get? Minus 2 times minus 2x, you get, this is number 2, I'm going to rewrite it, minus 2 times minus 2x, you get 4x, minus 2 times y, you get minus 2y, equal minus 2 times minus 4 is 8. Now, look, this is the second equation, this is the first equation. They're exactly the same thing. 4x minus 2y equal 8. 4x minus 2y equal 8. So they are the same thing. And that's what we said. So if in the process of solving you come up with the true statement, the left-hand side a constant equal to right-hand side, which is a constant, then you say the two lines are exactly the same thing. Therefore, you have infinite number of solution. Okay. If you solve in the process of solving the system, you come up with a statement which is not true. So 4 equal 8, or 4 equal 2, or 4 equal minus 8, or whatever. You come up with a statement which is not true. That means the two lines do not have any solution. Okay? Let me clean this up. So here, we said the two lines are the same. Therefore, infinite number of solutions here. Get everything cleaned again. They did the same thing I did. They figured out y in terms of, from the second one, they got y in terms of x, and in the second one, and plug it back into the first equation, and well, 8 equal 8, divide everything, or 0 equal to 0. You can cancel. This one would cancel. 4x would cancel with minus 4x. 8 on this side would cancel with 8 on the other side. So 0 equals 0, still the true statement. Right? So this is a true statement, so the equations are equivalent. They are the same line. Right? If you graph it, you're going to see they fall right on top of each other. Here's another one. Here's another system of equation. Let's solve this one. 4x minus 2y equal 3 minus 2x plus y equal minus 4. Okay? Again, let's figure out from the second one. From the second one, let's figure out y. Y would be equal to 2x minus 4. Plug this value into the first equation. So first equation would become 4x minus 2 times 2x minus 4 equal 3. So 4x minus 4x plus 8 equal 3. So 4x and minus 4x would cancel. What do you have? You have 8 equal 3. This is not a true statement. Right? 8 is not equal to 3. When this happens, that means the two lines do not cross each other. The two lines are parallel to each other. The two lines are parallel to each other. Right? I can show the two lines are parallel to each other if I can show the slope of the two lines are the same. So let's do that. Let's rewrite each one of these lines. Let's rewrite number 1 in the form of slope-intercept form. So the first one, I'm going to take 2y to the other side. It becomes positive 2y. So you would have 4x. Take to the 3 to the other side equal 2y. Divide everything by 2. then y is equal to 2x minus 3/2. I can write it this way also, y equal to 2x minus 3/2. It doesn't make any difference. So how much is the slope here? The slope is 2. Let's do number 2. Let's do number 2 here. Okay. Keep y on the left-hand side. Take everything to the other side. It would be what? 2x minus 4. This is this equation number 2. Y equal to 2x minus. You can see clearly that the slope for both of these lines is 2. So same slope, different intercept. So the two lines are parallel to each other because the slopes are the same. Right? So if you get statement which is not true when you're solving, such as 8 equal 3, which is not true, that means the two lines are parallel to each other and there is no common point. There is no crossing of the two lines, right? No unique solution. As usual, let's see what they have done. Again, from the second one, solve for y. Plug it in back into the first one. Simplify. Well, they took 8 to the other side. So 0 equal minus 5. Of course, it's not true, right? The statement is false. So the system has no solution. So if you come up with a false statement, that means the system has no solution. Now, what if you have 3 linear equations? How do you solve that? 3 linear equations. We're going to have the simplest form of solving, which is substitution, which is the same thing we did with a system of 2 linear equations. So 3 linear equations, we're going to do substitution also. Now here are the 3 equations. A1x plus b1y plus c1z equal d1, and then a2x, b2y, c2z. So here you see a system of 3 equations and 3 unknowns. The unknowns are x, y, and z. Everything else, a, b, c, d, they all are constant, right? Now, since we are dealing with 3 equations, then we want to graph this. You graph it on a 3-dimensional space. You will graph it in 3-dimensional space, right? So each one of these equations represent a plane, which is like a sheet of paper in space of a room, a sheet of paper. Now, again, you can have 3 possibilities. Number one, you can have these 3 sheets of paper. You can see the yellow one, the green one, the purple one. Each one of them is as a sheet of paper. They cross each other. At one point, there is one point here which is in common between all 3. There's one point which is in common between the 3 sheets, the yellow one, the green one, the purple one, this one, where they cross each other. That way you would get a unique solution. If that is the case, right, you would get a unique solution. Then another way is that these 3 sheets of paper, these 3 planes, cross each other on a line. If they cross each other on the line, a line has infinite number of x and y, infinite number of solutions. So you get infinitely many solutions, right? Everything on the line. A third possibility is that the three sheets of paper you have in the room, they are parallel to each other. That means they don't cross each other. If that is the situation, then the system of three linear equations does not have any solution because they are parallel to each other. So again, as it was with the case with two linear equations, here you have three possibilities. Number one, a unique solution. Number two, infinite number of solutions. Number three, no solution. Here it explains what a linear equation with n variables is. It says a linear equation in n variables, now the variables are called x1, x2, x3, all the way to xn, is in this form: a1 x1 plus a2 x2 plus a3 x3 all the way to an xn equal to a constant. Again, a's are all constant and x's are your variable and c is a constant, right? So if that is the case, then you would get a linear equation in n variables. So for example, you get 2x1 plus 5x2 minus 3x3 plus 12x4 minus 7x5 equal 18, for example, right? So this is a 5-variable linear equation in 5 variable. In this case, n is 5 because you have x1, x2, x3, x4, x5, 5 variables, right? One way to solve it is called the Gauss-Jordan method. Again, this is simply the substitution of solving from one and plugging it in the other two. Solving for one variable in one of these equations and plug it into the other two, right? Remember, you have a system of three equations. Interchange any two equations. It says replace an equation by a non-zero constant multiple of itself, and replace an equation by the sum of the equation and a constant multiple of any other equation. What does it mean? We're going to see that in action. Look here. You have x minus y plus z equal 2. I'm gonna show you what it actually means, and then when you see it, it might come a little bit clearer to you. In the first equation, we are going to solve for x. This is the simplest way of doing it. In the first equation, we're going to solve for x. So the first equation would be x equal, take everything to the other side. So it would be y minus z plus 2. That's the first equation. Then for x in the other two equations, we're going to plug its equivalent. So the second equation would now become minus, since it is a minus x, it would be minus y minus z plus 2 plus 3y minus 3z equals 0. Before I go further, I'm going to simplify this. So minus y plus z minus 2 plus 3y minus 3z equals 0. I'm going to now combine the like terms. I have minus y and plus 3y. That would be 2y. I have z minus 3z, that's minus 2z, equal, take the minus 2 to the other side, it would be a 2. That's going to be the second equation. Third equation, I will do the same thing. For x, I'm going to plug in its equivalent. This is I'm going to put this in the third equation. So it would be 2 times y minus z plus 2 plus y plus z equal 3. So that would be 2y minus 2z plus 4 plus y plus z equal 3. Now combine the like term. 2y and 1y would make it 3y. Minus 2z plus z would be minus z. Equal, take the 4 to the other side would be minus 4. Minus 4 and 3 would be minus 1. Now we are reduced with 2 equations and 2 unknown. These are the 2 equations. I'm going to write it here. 2y minus 2z equal 2, and 3y minus z equal minus 1. Now I have 2 equations, 2 unknowns. 2 unknowns are y and z. Again, as before, I solve for z here. Let's say in the second one I solve for z. I take the minus z to the other side. It would become z equal 3y plus 1. Z equal 3y plus 1. I go ahead and plug it back into the equation, into the first equation. This value, I'm going to plug it into the first equation for the z. So I would get 2y minus 2 times z would be 2 times 3y plus 1 equal 2. So 2y minus 6y minus 2 equal 2. So I get minus 4y minus 2 equal 2. So minus 4y equal 4. Therefore y would be equal to minus 1. Now I solve for one of the variables. Y is equal to minus 1. So if I go ahead and plug this y equal minus 1 into one of these 2 equations up here, one of these 2 equations, either one of them, I should get z value. So let's go ahead and do it here since I have it written here. So 3y would be 3 times minus 1 minus z equal minus 1. So minus 3 minus z equal minus 1. Therefore, z would be equal to, bring z to the left hand side, then minus 1 to this side, z would be minus 2. Z is equal to minus 2. So I got y value, I got z value. I go ahead and plug it into this first one, I get the x value. So x would be equal to y minus z plus 2. Y was minus 1. Minus z would become plus 2, since z is minus 2, plus 2. Therefore, x would be equal to 3. So the unique solution here would be x of 3, y of minus 1, z of minus 2. Hopefully I did everything correct. So this is where the 3 planes cross each other at one point, a unique solution. X value is 3, y value is minus 1, and the z value is minus 2. Here is a substitution. The Gauss-Jordan method is a little bit different than this substitution I do, but the gist of it is basically the same thing. So we're gonna see what they did with using Gauss-Jordan method, again, it should come up with the same answer. 3 minus 1, let me write this down, 3 minus 1 and minus 2. This is the unique solution that we come up with. Let's see it using Gauss-Jordan method, they come up with the same thing. Here to do the Gauss-Jordan method, they're gonna have each one of these three equations, three linear equations with multiple variables as rho 1, rho 2, rho 3. Here R1, R2, R3. So step number one, here is rho 1, right? And here 2y minus 2z, 2y minus 2z equal to 2, 3y minus z equal to 1, right? What they did is replace R2 with R1 plus R2. So the second row is the summation of R1 and R2. So if you add these two together, x here, if you add row 1 and row 2 together, which is this is what they have done, the minus x and x would cancel. 3y minus y would be 2y, and minus 3z and plus z would become minus 2z, there's minus 2z, and 0 plus 2 would be 2. So that's what they have done. In the third equation, it says replace R3 with minus 2 times R1 plus R3, minus 2 times R1, right? So you take row 1 here, minus 2 times R1. So you multiply row 1 by minus 2 and then add it to row 3. So let's do that. Minus 2 times R1, it would be what? Minus 2 times everything, right? Minus 2 times everything. So it would be minus 2x plus 2y minus 2z equal minus 4. Now when you add this one and this one, right? When you add them up, minus 2x and plus 2x would cancel. You have y and plus 2y, it would be 3y. That's what I have here. And you have z and minus 2z. That would be minus z. There it is. And then you have 3 plus minus 4. That would be minus 1. So what happened in the second and the third equation, we got rid of the x variable. And that was the objective. You get rid of one variable. Now you have two variables and two equations in these two. And that's basically the same thing we came up with when we did it with the substitution. So now you're going to eliminate another variable and solve for 1. So what do they do? You write the first one as it is. This is the first one, the first equation. You cannot do anything. You play with the second and the third equation. So what they do? Replace R2, which is this one now, with half of R2. So you multiply everything here. You multiply everything here by 1/2. So 1/2 times 2y is y. 1/2 times minus 2z is minus z. 1/2 times 2 is 1. That take care of this. And you can guess what, oops. Here, minus 3 minus z, they write it as is. Now, right, nothing here. Then you go and We replace R3 with minus 3 times R2 plus R3. Minus 3 times R2 plus R3. You get rid of, again, you're trying to get rid of the Y. You're trying to get rid of the Y, right? So if I go ahead and multiply this one by minus 3, so I get minus 3y plus 3z equal minus 3, right? Now this one and this one, I add them up together. When I add them up, minus 3, 3y would cancel. 3z and minus z would be 2z equal minus 3 and minus 1 is minus 4. That's what I should come up with, right? Minus 2z equal minus 4. Now you only have one variable in the second one, in the third one. So if minus 2z is equal to minus 4, divide both sides by 2, you get z equal to minus 2. Z equal minus 2. So that's the answer to z. You plug this z of minus 2 into the first one, you get the answer to y. Y would be equal to minus 1. This is replace R3 with 1/2 of R3, right? Y would be minus 1. And finally, in the first one, you replace it with z of minus 2, y of minus 1, h would be 3. Therefore, the common point is h of 3, y of minus 1, and z of minus 2. Okay? That's as far as you're responsible. So it's only section 5.1 in this chapter. This augmented matrix and beyond, we are not going to cover in this chapter. That's the end of chapter 5.